Lesson 4.3, Multiplying and Dividing Rational Expressions. In this lesson, we'll take a look at simplifying an expression that has polynomials in the numerator and denominator. We'll multiply and we'll divide. When asked to simplify a rational expression, we have steps to follow to complete that process. And if you remember anything about last semester, I love to give you steps to follow so that we can have a flawless plan. In step 1, what you'd like to do or what you want to do with a rational expression is factor completely. We'll take, hang on. There we go. We will factor completely. We'll take all of the factoring rules that we talked about in semester 1 and apply them here. Once everything is factored, we'll state restrictions in our denominator. And those would be values for x that would make the denominator equal to 0, which is not possible. Finally, in step 3, we'll reduce the fraction on top and bottom as long as there is an exact match to cancel out. And this process will carry with us when we multiply and when we divide. Let's take a look at our first example. Write an expression that is equivalent to x cubed minus 5x squared minus 24x all over x cubed plus x squared minus 72x. Since we have addition and subtraction, we cannot just cancel out terms. It doesn't work that way. If we follow our 3-step process, we should get the correct result every time. Step 1 is to factor completely. If I start with the numerator, we have x cubed minus 5x squared minus 24x. I recognize it's a cubic function, but I don't have to do p over q. All 3 terms have an x in common. I can factor that out. And if we do that, we get x squared minus 5x minus 24. So now let's see if we can factor even further. Can you break down x squared minus 5x minus 24? Split the c to add and multiply, or to add to get the b. 2 numbers that multiply to get negative 24 would be negative 8 and positive 3. That means we still have our x on the outside, and x squared breaks apart into x times x minus 8 plus 3. That's factored completely. Let's try the same thing in the denominator. Again, we have an x cubed, an x squared, and an x. All 3 terms have an x in common. We're left with x squared plus x minus 72. Now 2 numbers that multiply to get negative 72, but add to get positive 1 in the middle, would be positive 9 and negative 8. Keep our x out in front, and we have x plus 9 and x minus 8. That's all step 1, factoring completely. Step 2, state restrictions in your domain. Taking a look at all 3 parts in the denominator, we have 3 different x's. That means there are 3 possible x values that will make the denominator equal to 0. So what we'll do is we'll state all of them in our domain restriction. For that first x, if we set that not equal to 0, that's automatically our first restriction. For our second x, if we say x plus 9 can't equal 0, and we'll move the 9 over, that means x can't equal negative 9. In our final parenthesis, we have x minus 8. If we say it can't equal 0 and we add 8, that simply means x cannot equal 8 either. We have 3 different restrictions on x. X can't equal 0, negative 9, or positive 8. Once you've stated your restrictions in your domain, that means any other values for x would make that possible. We can simplify. Step 3 would be to reduce if possible. Taking anything on the top and the bottom that are the exact same, they'll cancel out. Notice on the top and the bottom we have an x and an x. They cancel out. We also have an x minus 8 on top and an x minus 8 on the bottom. They're the exact same. But then we have a parenthesis x plus 3 divided by x plus 9. And since those values don't simplify any further, they're not an exact match, that's the reduced form for your fraction, x plus 3 over x plus 9. And we include all three of our restrictions in our final answer. What is the simplified form of the rational expression? What is the domain for which the identity between the two expressions is valid? We're going to follow the same three steps that we did up above. But recognize something different here. Do you all see that in the top part, the x squared is second and it's negative? So what I'm going to do is actually flip that order around and put the x squared term first. But when I do that, I have to make it negative x squared plus 4. And then all over x squared plus 3x minus 10. To factor, in the numerator, it's easier to work with an x squared term when it's positive. That means the first thing I'm going to do is actually factor out that negative. If I put that negative on the outside, then I get positive x squared minus 4 on the inside. And that's the difference of two perfect squares. That's a definition we had back in semester 1. Keeping that negative out in front, if you have a perfect square minus another perfect square, that would separate into two smaller parentheses of x plus 2 and x minus 2. In the denominator, we have x squared plus 3x minus 10. Thinking of two numbers that would multiply to get negative 10, but add to get positive 3. What do you think? What are two numbers that would multiply to get negative 10 and add to get positive 3? If you thought positive 5 and negative 2, you'd be correct. That's as far as that factors, so we'll carry it over into our final factored form. And again, this is all step 1. Step 2 is stating restrictions in your domain before we simplify. Looking at just the denominator, what are the values for x that make that denominator not possible or make it equal to 0? If you said x plus 5 equal to 0, we'd say x can't equal negative 5. And if we say the same thing for x minus 2, saying that it actually can't equal 0, that means x would also equal positive 2. Those are our two domain restrictions. Last but not least, the fun part, reducing what we can if there's anything that's a match. The negative on the top, we're going to leave that. There's an x plus 2 on the top, but not a match on the bottom. Recognize that there's an x minus 2 on top and on the bottom. It looks like that's all we can simplify. Therefore, the simplified version for this rational expression would be a negative and then x plus 2 on the top, all divided by x plus 5 on the bottom. On the bottom, the parenthesis would be optional unless the directions on Pearson say to put it in a parenthesis for your answer. When asked to multiply rational expressions together, our process is going to be very similar to the parts up above. The first thing you'll do is you'll factor completely. This will be a pretty common theme. And then state your restrictions for your denominator. So far, it's kind of business as usual. Now, when you're asked to multiply, you really are just doing a simplify or a reducing process. Any numerator can cancel out with any denominator. Whoa, hang on. Any numerator, well, yep, got an E in there. Numerator, there we go, can cancel with any denominator, which means in one fraction, you may cancel out with another part of the denominator in a different fraction. And now we'll do a step 4. We're actually going to leave your answer in factored form. You wouldn't multiply parts back together again. We'll leave in factored form. Let's give a couple a try. Example A. What is the product of 2xy over z and 3x squared over 4yz? Whoa. All right, let's see what we've got here. So it's product. That means we're going to multiply. I'll take 2xy divided by z times 3x squared over 4yz. We're trying to find their product. The first thing you want to do is factor. And you factor when you have addition or subtraction. Looking at this product, it doesn't appear that we have anything like that. So we aren't going to actually have an answer in factored form this time. I know I said that before, but this one's a little unique. The second thing, though, that we'll always do is we will always state restrictions. Notice our denominator. We have a z all by itself, and then a y times z on the other fraction. If we say for that first fraction that z cannot equal 0, then that fraction is valid. In that second fraction, z cannot equal 0 still is part of that restriction, but we have another variable. We have to say y can't equal 0 either. Therefore, in our domain, we'd say x. No, we wouldn't say x. I'm just so used to saying x all the time in these problems. We would say y can't equal 0 and z can't equal 0. And then the denominators are set. We're good to go. Step 3, any numerator can cancel out with any denominator. So let's see what we can do here. I see this 2 and this 4. They can reduce by a factor of 2. 2 cancels itself out and 2 goes into 4 twice. What else do we have here? I see this y and this y, but we still keep our restriction in our denominator. So now if I look at this problem, there isn't anything factored, but I have an x in that first fraction over z times 3x squared over 2z. So when we multiply, we've done this before. The 3 on the top is going to stay, but if we take x times x squared, that makes the exponent go to x cubed. In the denominator, we keep our 2. Z times z is z squared. That would be our product for those two fractions. Now let's try one that requires a little bit of factoring. What is the simplified form of 5x over x plus 3 times x squared plus x minus 6 over x squared plus 2x plus 1 times x squared plus x over 5x minus 10? Step 1, we know what to do here. We're going to factor everything. That first fraction, we start off kind of lucky. 5x over x plus 3, nothing factors there. We can leave that as is. In that second fraction, x squared plus x minus 6, can you think of two numbers that multiply to get negative 6, but add to get positive 1? How about 3 and negative 2? They would multiply to get negative 6 and add to get positive 1. Therefore, we could split apart the x squared into x times x, and then positive 3, negative 2. In the denominator, what are two numbers that multiply to get 1? We don't really have a lot of options there. Two numbers that multiply to get 1 but add to get 2 would just be 1 and 1. We'll write x plus 1 over x plus 1. All right, our last round here. X squared plus x. I notice that there's no c value to try to split, but each term has an x in common. If you factor that x out, we would have x plus 1 left over. Finally, in the denominator, 5x minus 10, both of those terms have a 5 in common. And if we factor out that 5, we have x minus 2 left over. It looks like that's factored completely. All right, our next step, let's state restrictions in our domain. Take a look at each denominator that has an x in it. For that first denominator, x plus 3, I know that x can't equal negative 3. In that second denominator, the two parentheses are the same. X can't equal negative 1. We don't state multiplicities here because we're not sketching a graph. And in that third fraction, the only x I see is x minus 2. And that means x can't equal positive 2. And there's our domain restriction set. Now, again, the fun part, let's cross some things off. Let's see. If it's 5 times x, that means this 5 can cancel with this one, leaving x left over. I have x plus 3 on the top and an x plus 3 on the bottom. We have x minus 2 on top, x minus 2 on the bottom. Ooh, there's lots canceling out here. There's an x plus 1 on top. I have 2 of them on the bottom, but I can only cancel the same amount. So I can only cancel out one of them. What's left over in the numerator is the first x and the second x. And if we multiply those, x times x would equal x squared. In the denominator, all that's left over is that x plus 1. And that's multiplying rational expressions together. Tomorrow, we'll take a look at division.